think I'm waiting. Once it starts, I'll start. I'll introduce you yourself, and then we'll start.
Okay.
We are live.
Okay.
So shall we start? We are already online.
Yeah. Okay. So, hello everyone. Very good evening to all of you. I hope all of you are doing great. So, if I am clearly visible to you and clearly audible to you, please let me know in the chat box. You can put your answers in the chat box. I'll see it and I'll get to know. Okay, yeah. So you can just let me know whether I am clearly visible. Yes. Okay, so you can see me clearly and my voice is also clearly audible to you. Great. Okay. Again, a very good evening to all of you. Myself, Meet Panchal, and I will be your host of this webinar series by Nawaz Edutech. But do you know why we are organizing this webinar series? Can you let me know in the chat box why we are organizing this webinar series? Currently, we are following one very interesting thing. So you can put it in the chat box. What's the reason behind organizing this webinar series? Yes, right. You are exactly right. World Space Week. It's an annual celebration that takes place from 4th of October to 10th of October. It is celebrated in over 95 plus countries worldwide. It serves as an international recognition of the contributions of science and technology to the betterment of humanity. Now, to kick off our gathering, let's start with an interesting, fun question. Okay, so I have one interesting question for you. Suppose you are an astronaut and you are getting a chance to bring one person to space with you. So, whom would you take with you? Can you let me know in the chat box? Okay, you are an astronaut and you are getting a chance to take one person with you to the space. So, whom would you take with you? Will it be your parents? Will it be your friend? Will it be your school teacher? Okay. Or will it be your pet? Whom will you select with you? Okay, okay, great, great. Okay, yeah, very interesting answer, right? Some people are saying Abdul Kalam, Kalpana Chawla. Okay, so those are very interesting answers we are getting. That's excellent. Okay, and some of them are taking their teacher, some of them are taking their friend. That's great. Okay, we got such wonderful answers. So to boost up this energy, okay, we are privileged to have Professor Mayank Vahia, a prominent astronomer and educator with us today during World Space Week. A retired professor at the Tata Institute of Fundamental Research (TIFR) in Mumbai, Professor Vaya has dedicated his career to unraveling the mysteries of the universe and exploring the historical context of astronomical knowledge. Professor Vaya initially specialized in developing space telescopes for high energy astrophysics, but has since shifted his focus towards understanding the origins and evolution of astronomy, as well as its connection to ancient civilizations. His research interests span several domains, including astronomy and astrophysics, science education, and the history of the science. He has authored over 245 papers with more than 1,500 citations, reflecting his influence in various fields. Professor Vaya has written extensively on topics related to astronomy and education. His notable works include Physical Sciences and the Future of India, a book discussing the role of physical sciences in shaping India's future. Today, as he speaks on the scale of the universe, we can look forward to an engaging presentation that not only highlights the vastness of our cosmos, but also connects it with humanity's historical journey through science. And at the end of the lecture, I would like to request Sir to share his experience and how one can join the field of astronomy and astrophysics. So please, everyone, join me to welcoming Professor Mayank Vahia. Sir, over to you.
Yes, good evening, all of you. I hope you can see my PowerPoint presentation. It simply says Unity of Science and my name. Now, all of you, we all learn science in physics, chemistry, biology, mathematics, and variety of fields, geology, and so on. But really, nature has no such distinction between one field and another. There is an artificial limit division that we have created because we cannot really comprehend everything. And what I'm going to do today is to talk about the totality of the vision of nature and the working of nature using a series of slides which will highlight these issues. So, in each slide, you will see two numbers on the left. It says 10 raised to 0 meters and it says 1 meter at the bottom. And as you can imagine, the next slide will be 10 raised to 1 meter, the third slide will be 10 raised to 2 meters, and so on. And when we come to 1000 meters, we normally don't say 1000 meters, we say 1 kilometer. So the lower slide will change to 1 kilometer. So the second number will give you the number that we normally use for that kind of size scale. The first number will give you how much bigger a picture we are seeing. So we begin with 10 raised to 0. 10 raised to 0 is 1 meter. And what that means is that this picture is 1 meter end to end. And a typical human being is about 1.8 meters. So you can imagine if you have a box of about 1 meter by 1 meter around you, you will notice that that is your personal private space. We all like to own this 1 meter cube space around us. We don't like strangers within us, within that 1 meter cube. We don't like bad smell within a meter cube. We get irritated if there is a mosquito within a meter cube of us. A meter cube is our private space. Many of us apply perfumes and so on so that that 1 meter cube smells nice. And we like to own that 1 meter cube. That is our personal private space that we all like to have. So even when, I mean, if you're traveling by public transport, it's a different issue. Otherwise, in general, um, you would only have friends within a 1 meter cube of you. Only friends will be there within a meter cube, and if there is a stranger within a meter cube, you will feel uncomfortable. But the nature doesn't stop there. You can go to 10 meters. And sorry. And 10 meters is a slightly larger space. Typically, a classroom is a little bit less than 10 meter in length. But at 10 meters already, we can't touch, we can't taste, we can barely smell if the smell is really very strong, and we can hear and see. Hearing also is dependent on very loud noise. So, for example, if there is a lecture room in which there is 100, which is 10 meters in size, we like to have a mic, etc., to make it comfortable. So, even speaking continuous to somebody 10 meters away is difficult. We can see very well because humans are visual animals. We depend on our sense of sight as our primary sense, and therefore we can see 10 meters very clearly, provided, of course, there is no wall or something. So already two of my senses are completely useless, two are borderline, and I'm reduced only to seeing what is at 10 meters from me. You go to 100 meters, and this is a picture of my institute. 100 meters is a very long distance. In a large city like Hyderabad, the bus stops are typically about 100 meters away because nobody wants to walk 100 meters. 100 meters is irritating large. It's about 3 or 4 minutes of walk, and therefore we would like to avoid that. If your school is 100 meters from your house, then the chances are that your parents have bought you a bicycle or something to travel, because 100 meters is an irritating distance. And so, for example, if you want something that is available in a shop 100 meters away, chances are that you will try to do without it rather than go all the way, buy it, and come back. So at 100 meters, just the third slide from where I started, we are talking about large irritating distances. But you can go to 1 kilometer, and 1 kilometer is a very large space. We really cannot comprehend 99% of what is happening within 1 kilometer, square kilometer of you. We would know the map. We would not get lost in 100 in 1 square kilometer area because we would know all the lanes and streets. But really, we would not know some of the shops, and we would definitely not know most of the people living within a square kilometer of us. At 1 kilometer, I have now lost complete comprehension of that area, except maybe for streets and so on. At 1 kilometer, now the world is too large for me to really fully comprehend. You go to 10 kilometers, and then you actually come to a second limit. So 10 kilometers or 10 kilometers is 100 square kilometers. This is my city of Mumbai, which is very odd because it is at width, it's only 5 kilometers, and its length, it therefore can go much further. But at 10 kilometer by 10 kilometer, 100 square kilometers is where you come across another limit. No human cities are typically bigger than 100 square kilometers. If they are small, bigger than 100 meters, 10 square kilometers, then they are divided into smaller cities. So Hyderabad and Secunderabad are separate. Mumbai has Thane, Vashi, so many other regions, each of them worthy of being a city of their own. And therefore, they are divided into smaller cities. Because at 10 kilometers, we now reach a limit of how much we can comprehend. We, of course, talk about state and nation and all that. But when you think about it at 10-kilometer level or 100 square kilometers, is where your municipality operates, and your municipality provides you with water supply, drainage system, security, it manages trade and everything within your area. And so at 100 square kilometers, a typical city exists. If the city becomes larger than 100 square kilometers, it has to be divided into smaller cities. And this is true world over. It is not just a question of India. So at 1 kilometer, I said I lost track of how big it is. At 10 square kilometers, at 10 kilometers, I said now it is genuinely too large for anybody to keep track of. But at 100 kilometers, now the whole human ability to organize anything is strained so much that anything more than 100 square kilometers is actually divided into smaller cities. You go to 1,000 kilometers, 100 kilometers, that is 100 kilometers by 100 kilometers, you now reach a second limit. So this is the picture that I had shown you earlier. And as I told you, Mumbai is divided into smaller cities like Thane, Vashi, Kalyan, Ulhasnagar, and so on. And people routinely travel from these places to Mumbai to work. But at 100 square kilometers, you reach another limit. So if you think about it, you imagine somebody from a city 100 kilometers away from you comes to you and starts talking to you. You will realize very quickly that that person is not from your city. At 100 kilometers distances, you tend to lose track of things. You use words differently, you use vocabulary differently, you speak differently. At 100 kilometers, essentially cultures change. Irrespective of how well you can travel between these two cities, etc., at the end of the day, at 100 kilometers, the human culture disintegrates. It becomes very different from place to place. So at 1 kilometer, I reached my personal limit. At 10 kilometers, I said my municipality lost track. At 100 kilometers, I'm saying cultures also disintegrate and people behave differently if they are 100 kilometers apart. But nature, of course, does not stop at 100 kilometers, it goes to 1,000 kilometers. And at 1,000 kilometers, you see something very interesting. So this is the coastline of India, and this is where Mumbai is. But the entire Indian population of Mumbai at 18 million people or so is not even worthy of a single spot on this pictures. At 1,000 kilometers, human beings are completely irrelevant. The only thing that matters is that the water has higher specific heat than land. So for the same amount of water, sunlight falling on Earth, the water can absorb a lot more heat without getting hot, while the land gets hot very quickly. As a result of which, the air above the land becomes hot very quickly, and therefore the cool air from the river seas comes as a breeze into the land, and with it, it brings a lot of water, and therefore water is distributed all over the land simply because specific heat of iron or land is different from specific heat of water, and that is the only thing that matters. At 1,000 kilometers, for all our pride and arrogance, human beings are completely irrelevant. Your entire modeling depends on the exact geometry, exact geography, and the fact that the specific heat of water and land are different. Wherever the water fails to reach, of course, you have deserts. Wherever there's plenty of water, you have plenty of greenery. But that is all that matters. To spoil this dynamics, you have to pump obnoxious gases over hundreds of years to spoil something. But that's a different story. Essentially, this is a very stable structure and system. You go to 10,000 kilometers, and now you reach the edge of this Earth. Earth is about 12,000 kilometers in diameter, so you get most of the Earth within this area. And this is where I began my story. And you realize that the specific heat story actually goes very far in the sense that the Earth's orbit is inclined at 23.5 degrees to its orbit. And therefore, when there is winter in northern hemisphere, there is summer in the southern hemisphere. And because southern hemisphere for India is all water, a lot of this water evaporates during October, November, December, and then as January, February comes, the water comes that clouds of water move to central India, center of the earth near equator, and eventually in July they come and hit India. So in the monsoon of India has very little to do either with Arabian Sea or Bay of Bengal. It has everything to do with southern and central Indian Ocean. If, for example, if Australia was not this far away further east, and if it was over here, essentially we would have an Africa-like situation in the sense that there would be no evaporation in December, January, and therefore there would be no rainfall in June, July, and we would essentially have a desert where today we have such a thriving nation or thriving subcontinent. This piece of so that is all that matters, the amount of heat that erupts, and of course the fact that there is a lot more landmass in the north than in the south. As the summer comes, the landmass of India of Asia essentially becomes hot very quickly, and therefore the moisture movement happens very quickly, and that is how we get our monsoon in June, July. You put Australia over here, and everything is destroyed. You remove Himalayas, and these the evaporated water clouds that come would simply pass on to Tibet and beyond. You take this piece of rock and do anything with it, and you spoil its chances of having life. You say make it 20% smaller than what it is, and essentially all atmosphere would disappear. You make it, say, 10% bigger than what it is, and our own weight on Earth would be so much that we would struggle to walk. You take this piece of rock and move it 10% closer to the sun than it is, and essentially it would be so hot that all the water would sizzle away. You take it 10% further away from the sun, and it would be so cold that all the carbon dioxide would freeze, and essentially there would be no life on Earth. Uh, and you change this 23.5 degrees tilt and make it say 0 degrees. Essentially, there will be no summers and winters. There will be no movement of moisture into the inlands, and therefore life on Earth would be only restricted to the coast and water itself. This atmosphere has 75% nitrogen and very little of oxygen and other gases, and that is critical because if you increase the oxygen content by 10%, essentially a single fire in one single place would burn up the whole earth. You have to have an inert gas environment for the earth, life on earth to survive. You change that ratio and increase carbon dioxide, and we all know greenhouse effect and how much damage it has done already. This piece of rock and its dynamics is so delicate that 180 degrees away in north of South America, if there is an El Nino, a 3-degree increase in temperature in summer, essentially the monsoon on India will be spoiled because that place 180 degrees away will become warmer, and therefore all these moisture carrying clouds will be drifted towards the El Nino, the north, southern America, and we would have a very poor monsoon in our June, July, August. Essentially, this piece of rock is so delicate and so very well delicately surviving that almost anything you do to this earth, you spoil its chances of having life on earth. You realize that one single comet hit the earth 65 million years ago, about a couple of kilometers in size, and destroyed 90% of life on earth, including all the dinosaurs. Because of the fact that we have Jupiter and Saturn protecting us, such collisions are very rare. They typically happen every 100 million years or so. But without Jupiter and Saturn, such collision rates would be typically once every few thousand years, and life on Earth would not be possible. Almost anything that you do to this piece of rock, and you spoil its chances of having life. And there is no piece of rock like this anywhere in the universe. We know of thousands of planets around thousands of stars, but we have never seen anything like this. The bottom line is this is a very rare and delicate piece of the universe, and we should be taking great care of it. That we are not taking great care of it is a different part of the story, and it has led to so many disasters already, and we don't know how many more disasters are waiting for us. Remember that when dinosaurs became so very too large for their own good, a single comet impact was all that nature used to wipe them out of the earth and start life again. The biggest mammals at the time of dinosaurs were about the size of a rat. If they had been bigger, they would have been eaten by dinosaurs. Yeah. So the dinosaur life had to be removed from Earth before humans could come into being. And nature can as easily solve the problem of humans being a nuisance. Basically, we have proven ourselves to be cancerous on this globe of Earth. We have been reckless, we have been careless, we have been dumping things, we have been isolating things that should not have been isolated, like uranium and all that, at one place, which can be really dangerous. We've been doing so many things that are really not conducive to keeping the planet stable and good. And nature gets eventually irritated, nature can as easily wipe out humans as she wiped out all the dinosaurs and all the other lifetimes some 3 or 4 times earlier in the history of the Earth. The life on Earth is about 3,000 million years old, and we know of at least 4 times when nature simply got fed up of the design that was going on at that time, wiped out that sample, and created new set of life forms. So we should not take nature for granted. We should not take this globe for granted. We should treat it as a delicate and sensitive object that it is, and we should do everything to save it rather than recklessly exploit it for our short-term gains, because the long-term disasters can be genuinely very bad. But we are not doing it, and that's one of the tragedies of human life. But anyway, 10 raised to 7 meters, this is what the universe looks like. You go an order of magnitude up, and the first thing you notice that at 100,000 kilometers, you really don't see anything else. Even the moon at 300,000 kilometers is quite far from us. So take a box into which you could fit the Earth, make it 10 times bigger, and there is nothing else in it. It is empty. And you need to go another order of magnitude before you can see the movement of the moon and the orbit of the Earth. Earth takes about 2 months to travel about what root 2 million square million kilometers, and the moon takes 27 and a half days to complete one circle. Essentially, on this size scale, we are um, just the moon, Earth, and moon, and a period of about 2 months is shown. You go another order of magnitude up, and then you don't see anything else either. At a picture that is thousand, I remember I started with the Earth here. So 10 times bigger, 100 times bigger, 1,000 times bigger, 10,000, 1,000 times bigger, and you see nothing. It is like saying that if I take a box of 1 meter by 1 meter by 1 meter and put a speck of dust which is just 1 millimeter in size, the box is full. And that is all we are, 1 millimeter size speck of dust on a one cubic meter box. The universe is empty on this size scale. You go another order of magnitude up, and then you can see a little more. So from the last picture, I have increased the volume by a factor of 1,000. I've increased the linear size by a factor of 10, so the volume by 1,000. And you can see a bit of orbit of Venus and a bit of orbit of Mars. Venus is roughly Earth size, and Mars is about one-sixth the Earth size. So essentially, I have increased the volume or the amount of material by a factor of about 2.5, but I have increased the volume by 1,000. If you had one of those old generation 8-digit calculators, the average density would come out to be zero. That is how empty the universe is. And I'm just 10 raised to 11 meters from where I started, just 100 million kilometers. You go another order of magnitude up, and now you can see the inner solar system. So we have the Sun, Mercury, Venus, Earth, Mars, and bit of orbit of Jupiter. And I already told you how critical this Jupiter is so far from us. And because humans no longer use distance of kilometers, we now use a unit called astronomical unit. One astronomical unit is the average distance between the Earth and the Sun, and this is about 7 astronomical units. And you realize that the sun actually is not as large as is shown here, but just to make a point that the sun is here and all the orbits go around the sun. You go another order of magnitude up, and now you can see the whole solar system. So there's Mercury, Venus, Earth, Mars, a bit of Jupiter, Saturn, Uranus, and Neptune, and the solar system comes to an end. All the major planets are done. Pluto is not a planet, so therefore it doesn't count. But at 70 astronomical unit, at 10 raised to 13 meters, we now have a box that is big enough to fit the entire solar system. And the question that you can ask is, where is the nearest star? You go a factor of 10 up and you see nothing. You go a factor of 100 up and you see nothing. You go a factor of 1,000 up and you see nothing. Again, that same factor of 1,000 that we see in Earth, and you go to a factor of 10,000 to see a handful of other stars. And then you can see the stars closest to us. Proxima Centauri, which is in fact so faint that you can't see it without a telescope, but Alpha and Beta Centauri you can see without a telescope. Then there is Fomalhaut, there is Altair, and the brightest star in the night sky, Sirius. But now the distances are so large that even though light travels at 300,000 kilometers per second, it can go around the Earth 3 times in a millisecond, is also too slow. So, for example, if you ask me, sir, what does Sirius look like as of 5th of October 2024, I can't give you the answer. I can only give you the answer that if you go out and take a look at it, you will see Sirius as it was on 5th of October 2019, because even light takes 5 years to travel from Sirius to Earth, even moving at 300,000 kilometers per second. There is no such thing as now anymore. There is no such thing as just now something is happening. Because even from sun, for example, light takes 10 minutes to reach. So if the sun was to die, we would not know for 10 minutes that the sun is dead. But if Sirius was to die, we would not know for next 5 years that Sirius is dead. The distance now are genuinely astronomical. At 10 raised to 17 meters, even light takes 10 years to travel this distance. Astronomers use another unit called parsec, but we will sort of not bother about it. This light takes 10 years to travel this distance. That is how big this is. You go another order of magnitude when you see more stars. And most of the stars that you see in night sky come from within about 100 light years. There are a few very distinct exceptions, but I will come to those a little later. But this is roughly your visible sky. If you don't have a telescope, most of what you see would be restricted from within about 100 light years or so. And even there, about 60-70% of the objects you would not see without a telescope. You go another order of magnitude up, at 1,000 light years, you still see more stars. And if you think I'm going to just continue showing you more stars and more stars and more stars, you'd be surprised how different it is. Because if I go to 10 raised to 20 meters, now even the stars are so small that I can't see stars. I have a city light effect. Wherever there are lots of stars, I can see a white patch. And wherever there are very few stars, I can see darkness. And where there are really very no stars, you get a black picture on the top and bottom. And as you have imagined, as you have realized, the Earth and the solar system sit in the center of this box. So this is where we are. And this is the Centaurus arm. This is the Scorpius arm. This is the Centaurus arm. Sorry, this is the Centaurus arm. This is the Scorpius arm. So the constellation of Scorpio would be somewhere here. The Centaurus constellation would be over here. And the center of the galaxy would be, as I will show you in the next slide, along this line. We sit in a region which is very quiet. And that is why 1,000 times as big a box as solar system is devoid of stars. If you put a star within that box around the solar system, over a period of time, it would completely destroy the solar system because the gravity of the other stars would sort of nudge away Jupiter and Saturn, and eventually the whole solar system would be destroyed. So if you are in one of these regions which is dark, which is full of stars, really you don't have a hope of having a stable planetary system. We are fortunate that we are here. Another interesting thing is that the sun has not always been here. Unlike most stars, which are roughly where they are, sun has not been here. The sun is a gypsy. It is traveling along this diagonal at the rate of about 250 kilometers per second. 250 kilometers per second. The entire solar system is traveling along this diagonal. So, while the entire human race has come on Earth, while the Earth has traveled a distance less than the width of this laser point. Because even if 200 kilometers per second sounds very large, you are also talking about 10,000 light years as the distance. So the Earth was dominated by dinosaurs when the Earth was over here. Today we are over here, and we have no idea what life will look like when the Earth, when the sun goes is over here. It's about a few 100 million years is what it will take. And if the dinosaurs had been sort of good astronomers, they would have seen the Orion Nebula beautifully in their sky, and their day would have been 23 hours long. And today, of course, we have 24-hour day and a nice empty sky to look at, and then the sun goes on. You go another order of magnitude up, and now you can see the galaxy. It is 21 orders of magnitude bigger than you and me, and the light takes 100,000 years just to cross this unit. So there's a huge black hole, a star a million times the size of the sun, fitting in an area of less than the size of the solar system, and therefore its gravity is so strong that even light will not escape from that object. And that such an object sits over here, and all our stars are performing a circular dance around that galaxy. And we are this entire arm of the galaxy. Even as the sun keeps moving to diagonal, it is still forced to go around the sun, around the center of galaxy. And again, the number roughly is 250 kilometers per second. And you have this Jamin Chakri kind of an effect where if you it is as the galaxy moves clockwise, you have these drags on the movement, and therefore you can see a Jamin Chakri like effect. Except that this Jamin Chakri is very small compared to what you do, very slow compared to what you see in Diwali, because it takes about 250 million years to go around this. 250 million years. So we are here when the solar system is here. When it was opposite side to where we are right now, or rather when the galaxy had turned halfway, it was Jupiter's. It was the dinosaurs that ruled the Earth, and 400 million, 500 million years ago, it was still the dinosaurs. And eventually, nature decided that she had had enough of it, and eventually, the entire solar system would have been about a few degrees off from its current position when dinosaurs disappeared. At 10 raised to 21 meters, at 100,000 light years, this is what our universe looks like. In the sky, it looks like a river, and therefore we call it Milky Way, a path of the milk, and therefore it is called the Milky Way galaxy because it is our galaxy. You go an order of magnitude up, and by now you realize that the Earth is not a very important object in the universe. So if the Earth is not an important object in the universe and still manages to have a moon of its own, obviously a galaxy-like object of ours will have moons of its own. And we have, by the last count, about 15 satellite galaxies. Galaxies so small, like the moon to Earth, that they are really captured by by the gravity of Milky Way, and they go around the Milky Way galaxy. Exactly like that moon goes around the Earth, except of course that the time scales are astronomical. So they would not even have finished 10 rotations around the Milky Way galaxy over the entire lifetime of the universe. And that is when you see these two objects, the second and third farthest objects that you can see in the sky. This is called the Large Magellanic Cloud, and this is called the Small Magellanic Cloud. These are two dwarf galaxies that you can see without a telescope from Earth. To see the Large Magellanic Cloud, you have to go to the southern hemisphere, but Small Magellanic Cloud can actually be seen in the southern skies in India. So these are two satellite galaxies. But this is not the farthest object you can see without a telescope. The farthest object you can see comes next. So at 10 to 23 meters, 10 mega light years, you now have an interesting universe. It consists of about 30 galaxies, all of them, of course, making random movements, but none of them have enough velocity to escape from this grip of the common gravity. So, as Newton would have been happy to note, these galaxies are all bound within this circle. So, there is this big circle cluster of galaxies, about 30 galaxies, which are moving around each other, doing nothing in particular, but they can do very little because they are all bound by the common gravity. The only major event that is scheduled to happen is that the galaxy nearest to us is called the Andromeda galaxy. And it is, in fact, bigger than our own galaxy, and it is the farthest object you can see without a telescope. And Andromeda galaxy and Milky Way galaxy are scheduled to collide about 3 billion years from now. So if you're planning to be around, you will see one spectacular vision in the sky where this galaxy will cover almost the entire sky at night. But 3 billion years, we have no idea whether the sun will still be alive or not. And it's a long time. So it's going to be a spectacular event, but we don't know whether there'll be life on Earth to witness that event. But by now, you would have realized that the Earth is so insignificant and life on Earth is so insignificant that nature doesn't care. It moves at its own cycle. But the only interesting event to happen in this region of the universe is that these two galaxies are going to collide about 3 billion years or 3,000 million years from now. You go another order of magnitude up, and now you can see this local group are the 30 galaxies that I was telling you about. But there are other large clusters of galaxies. So this is about 100 million light years. And you can see that in the constellation of Centaurus, if you turn a telescope, you'll see a large cluster of galaxy. In Pavo Indus, if you turn your telescope, you will see large clusters of galaxy. And there are these large clusters of galaxies which consist of thousands of galaxies. One galaxy is a trillion star, and 1,000 galaxies are 1,000 trillion stars that make our local neighborhood. A local group, like I said, 30 galaxies, but these are really large galaxies. The interesting thing comes when you go to the next picture. And this picture is remarkably familiar. If you take a bucket of water and put detergent in it and rinse it, you get the same picture. You get bubbles. And these are great bubbles and the great froth from the birth of the universe. So there are regions where there is void and there is very little by way of material. And there are regions where hundreds and thousands of galaxies cram together and make a spectacular filament. And you can see this filament-like structure. The soap on Earth is made from electrostatic forces between molecules of the soap, while in the universe they are made by gravity in attraction between various objects in the universe and the froth from the birth and the conditions from the birth of the universe. The universe was born in a Big Bang 13.7 billion years ago, and this is the froth that comes from there. You can see the universe, in fact, to an order of magnitude bigger, and this is the largest picture of the universe that I can show you. And again, so the Earth and Milky Way galaxy is here, and this is the scan of the sky in a particular region of the galaxy, about 80 degrees, about 120 degrees or so. And this is the depth or the distance, and you can see that there are regions where there are clusters of galaxies, and there are regions where there are voids. Forget these pictures; these are artifacts of our inability to observe some region. Because if there's an obstruction here, you would not be able to see this. But this is the largest picture of the universe I can show you. Each dot is a galaxy. Each dot is somewhere between 100,000, about 100 million to a trillion stars, and all of them in this beautiful web that we call the universe. At 10 raised to 26 meters, at 10 raised to 10 light years, this is the largest picture of the universe I can show you. The universe is about 10% bigger than this, but when it was born, it was so dense that all the light from that period has been absorbed within that material, and therefore there is no light coming from that period of time. So the best we can see is 10 raised to 26 meters or 10 raised to 10 light years. Remember, I started with 10 raised to 0 meters and said by the time it was 10 raised to 3 meters, I lost my comprehension. And the Earth came to about 10 raised to 6 meters or so. And the universe actually extends to 10 raised to 26 meters. So you come back. 1 meter is more comfortable, 1 meter is more understandable, 1 meter is more acceptable, and therefore we are back to 1 meter. Now let's see what happens when you go down. So you come to 10 centimeters. 10 centimeters is very familiar to us. 10 centimeters roughly is this is the palm of my hand. And in English, there is a saying that if you know something very well, you know it like the back of your hand. Because at somewhere, sometime we were bored enough while sitting in a bus or while trying to study that we have stared at the back of our hand, and we all know the back of our hand very well. So 10 centimeters back of the hand, not a problem. You go another order of magnitude down and you see 1 centimeter. And already the picture does not look very pleasant. So what, edge to edge, this is 1 centimeter. But if you have elderly relatives, or if you looked at your own skin with magnifying glass, or if you remember your biology teacher telling you about sweat glands, etc., at least I can convince you that at 1 centimeter, this is what our skin looks like. You go an order of magnitude down, and then you come across 1 millimeter. 1 millimeter is a genuinely small scale which we can barely see. So if I was to ask you to draw a line which is 1 millimeter exactly in size, you won't be able to do it. Our motor senses are just not good enough. You will, even if you take this 0.5 mm pencils, you will either overshoot or undershoot because 1 millimeter is beyond our ability, our motor abilities to draw. At 1 millimeter, we have reached the limit of what is the size we can comprehend. But the universe, of course, continues. It is complete disregard for humans. And you come to zero point 0.1 millimeter. And this is an interesting universe. On Earth, we have 6 billion people, and we think the Earth is extremely crowded and something needs to be done. Your skin has 250 million germs living within these crevices. 250 million germs per person. So next time your teacher tells you to go and stand alone in the corner, tell them, teacher, it is impossible because it will be 2 million germs plus me going into the corner. And this is crowded. It is completely filled to capacity. Typically, these are single-celled organisms, so they can evolve and approach, sort of evolve very quickly and fill up the space. They can multiply very quickly and fill up the space. But there are interesting consequences. So, for example, if I was to shake hands with somebody, some germs from my hand will go on to that person's hand. Some germs from that person's hand will come to my hand. And because these germs have come from elsewhere, they will try to survive on your hand. And they will start one hell of a violent war in the universe. We don't appreciate it. We shake hands as friendliness, but fact of the matter is that we are irritating the universe on a massive scale when we shake hands. These germs, of course, are trying to get under your skin. The skin, therefore, has 7 layers to make sure that these things don't get in. But occasionally, if you have a cut in the skin or something, some of them go in which case, of course, the Earth's defense system makes sure that they do not do any harm to us. These germs live on the moisture in the air and the sweat that you produce. And their food is typically the dead skin cells. And the skin cells have a life expectancy of about 15 days. So if you have a wound, it gets repaired in 15 days anyway, because those cells were due for repairs. So they live by the dead skin, and they live by water and moisture. So every time you exercise, you essentially give each of them a house with a swimming pool. They're very happy, they multiply very quickly, and they give you that characteristic stink of sweat. It is not your smell, it is the smell of all these germs who have got together on your skin, not under your skin, on your skin. And this is how crowded the universe is at zero point 0.1 millimeter. You go down another order of magnitude and you come across one of the most beautiful objects in the universe. Now, I'm a physicist and I don't like to admit it, but this is one of the most complicated objects in the universe. It's a single cell of a body. And the single cells are really complicated entities in the sense that, suppose, let us assume, since this looks white, that this is a white blood cell. If it's a white blood cell, it is supposed to fight infection. Now, you and I, our laboratories, etc., can see a germ, etc., and worry about it. The single cell does not have a way of seeing anything. It doesn't have obviously eyes and hands and stuff like that. But it has a very peculiar skin. And for each white blood cell has a particular negative image of a particular virus. So, for example, when I was an infant and I was given this BCG vaccine, or when you took COVID vaccine or something, essentially what you did, you trained your bone marrow to create white blood cells whose skin is an exact negative replica of the infection that is about to come. And when that infection comes, this white blood cell will roll over it and both of them will lock, because one is a negative image, one is a positive image, and the two will get stuck. And the moment the two get stuck, body knows that this particular infection has come and it will start its reaction. It may start the reaction of either heating up the body when we get fever, or it may send poison to kill the infection that has come. And in extreme cases, a whole bunch of white blood cells will get together, form a cluster, trap all the viruses inside, and release a lot of poison and kill everybody, including themselves. And that is when you get a cut, you get pus, because it is essentially the dead white blood cells who sort of sacrifice themselves so that you could survive. You are talking about white blood cells at 10 to minus 5 meters. And they are your first lines of defense, or they're the most important line of defense that you have. These white blood cells are that complicated. That alone would merit, of course, the dispatch of distinction, but there is even more fascinating. So, for example, there are capillaries in my body which are smaller than 10 to minus 5 meters. Now, I am about 1.8 meters tall, and if I have to walk through a tunnel which is 1 meter tall, I would sort of bend and crawl and go through it. So these white blood cells are and essentially deform my shape. From a tall vertical shape of 1.9 meters, I would become less than 1 meter. So these white blood cells are required to go through these kind of tunnels. So, but their entire information is on their skin. So the cells are required to be as flexible as a water balloon, but as rigid as a wooden piece, so that the signal on the skin is not lost. And the way nature solves the problem is that she fills it up with jelly. So there is a jelly-like substance, and if you've eaten jelly, you know that if you sort of shake the jelly, it deforms itself. But when you release the force, it comes and regains its original shape. So that is fine. You fill it with jelly is just an interesting solution. But the interesting thing about jelly is custard. You can never ever put custard inside a jelly. It will always be outside the jelly because the viscosity is so much that you can never put anything inside. But within these cells, there is the nucleus and the whole bunch of chemistry that is going on, for which you need to provide energy and from which you need to remove garbage. So these cells are simultaneously rigid and yet active inside, and therefore they have to be contacted. And the way the white blood cells or any cell in the body solves that problem is the same way in which the city of Hyderabad solves this problem, which is to set up railway lines. The food and everything comes from a long distance through railways, and trucks, etc., carry the garbage out. So within these white blood cells, there are railway tracks, and they obviously cannot be made of metal and coal and stuff like that. They are made of molecules, and they're typically made of X-shaped molecules. The X shape, the top of that X is sensitive to the molecule which it is supposed to carry, and the bottom of the X is free. So when you put a particular molecule that this is supposed to carry, this wagon is supposed to carry, the bottom of the X must start walking, but it cannot walk at random because it is required to reach a destination. So nature sets up railway tracks within your cells so that these cells will move to correct distance and come back, or correct location and come back, either delivering food or removing the garbage. You are talking of railway lines on the size of 10 raised to minus 5 meters in 250 million cells in your body so that you and I can live. The result is that these cells don't live very long. The most shortest lived cells in the body, of course, are the skin cells, which live for only 15 years. And even in those in the brain, for example, don't live more than 25, 30 years. So by the time you become 25 or 30 years, really you have got nothing from your parents except the blueprint on which your life will be made. And that blueprint is itself very fascinating. And I'll just come to it in a minute. You go in order of magnitude and you can see the skin of the cell. And if you focus further, you can see that it is not opaque. It is a mesh, except that the mesh itself is so small that not even water molecules will escape. And therefore, for all practical purposes, it is solid. But with this, you can play chemistry because it's all chemistry. You can play chemistry with it. So you can imagine that I bring a molecule on the side so that this molecule feels attracted towards that one. When that happens, this whole entire area opens up, and then you can dump your food and you can transfer whatever you want inside the cell, or you can remove the garbage from the cell, and then you can remove this molecule, and this will close back on itself. You are talking of molecular keys on the size scale of 10 raised to minus 7 meters in 250 million cells in your body for you and me to work. That is how complicated life is. You go in order of magnitude now, and then you can see the manual that makes life. And the manual itself is a fascinating story. I don't have too much of time, so I will try and rush through it. But essentially, this is like a ladder. And you have the two legs of the ladder and the steps of the ladder. And the distance between the step of the ladder is very peculiar. And that distance can be only overcome by another molecule which has the correct shape. And therein lies all the information. So, for example, there is within this DNA, there is an instruction which decided the colors of my eyes. So when that instruction was read, the distance between the molecules was such that the molecule that came out was had a black color, and therefore I have black colored eyes. If there was a slight difference in the distance between the legs, essentially I could have had blue eyes, green eyes, red eyes, or anything depending on the molecule that could be made. And the complete information about my life exists in this DNA, and the DNA exists in every cell in my body, including the nails which I'll chop off today evening. That many copies are. you have. But this molecule is very long, and you cannot store such a long molecule in a cell. So what nature does is she takes the ladder and twists its one, which is first helix, and then forces into a second helix, which makes it such a compact molecule which can be carried. But it also means that this compact molecule cannot be read. In order to read it, this double helix must be opened into a single helix, and a single helix must be opened into a ladder, and that ladder must be folded so that we can read the steps between the distance between the steps in order to make the molecules of life. That is how complicated the manual of life is. You go in order of magnitude down, and this is what I mean by saying that typically the DNA molecule has these two legs, and then there is spacing between molecules, and this spacing decides what the information is. And that is how life works. The interesting thing is that the entire field of chemistry is a study of the universe on the size scale of 10 raised to minus 9 meters. You go to 10 raised to 10 meters and it becomes physics. When you go to 10 raised to 8 meters, it becomes biology. The entire study of universe is just one order of magnitude out of 42 orders of magnitude that make up the universe. You go another order of magnitude down and you see the atom. And the interesting, and if I was an honest man, actually this picture should be completely black. Because as you will see, the nucleus is much, much smaller than this atom. And what is plotted is that if you put a nucleus in the middle, you would find the electron within about an angstrom of that distance, or zero point 0.1 nanometer from the center of from the nucleus, and therefore we say that the atom is of this size. You go in order of, so the question is, how small is the nucleus? You go a factor of 10, you see nothing. A factor of 100, you see nothing. Factor of 1,000, you suspect that there is something. And factor of 10,000 is when you can see the nucleus. It is like saying that if I have a 1 meter house every 10 kilometers, I declare that place as full. 1 meter house every 10 kilometers away. And then you suddenly realize that nature, what is important to nature is forces and not material. In the sense that this nucleus, through its electrons, talks to another nucleus 10 kilometers away, and that together they are bound together in such a way that, for example, you don't fall through your chair, even though it is just one part in 10,000 of matter and most of it is empty space. Because the bond between them is very strong. And that is what makes the stable universe. Another interesting thing is that if you forget isotopes, there are only 92 such nuclei existing in nature, out of which beyond 85 they are unstable, so they are lead, and essentially beyond iron, that is 26, there are very few of them. So there are just 26 different nuclei on the size scale of 10 raised to minus 14 meter that govern what happens to the universe on 10 raised to 24 meter size scale. 38 orders of magnitude. That is how integrated the design of the universe is. You go an order of magnitude down, and this is the smallest picture of the universe that I will show you. We know that the protons and neutrons of the nucleus themselves consist of quarks, which are bound together in a very strange force, which does not allow them to go free, and therefore they are always bound to to a particular proton or a neutron. If you force it to break, it will go and connect and form another proton or neutron on time scales of 10 raised to minus 16 meters or so. Sorry. So that is the smallest part of the universe that I can show you. In principle, we have tried to look at even smaller sizes without much of a success of understanding what is going on. So just let us quickly look at what I was saying. So 10 raised to 0 meters is a human being, 10 raised to 3 meters is a mountain, 10 raised to 8 meters is a moon, 10 raised to 13 meters is the solar system, and we can go up to 10 raised to 30 meters, which is the 10 raised to 28 meters, 24 meters actually, which is the largest structure in the universe, or 10 raised to 25 meters. On the smaller skies, 10 raised to minus, sorry, 10 raised to minus 7 meters is the DNA, 10 raised to minus 12 meters is the nucleus. Atom, 10 raised to minus 7 meters, 17 meters is the smallest structures in the universe that we have seen. But really, our theoreticians tell us that the smallest structures in the universe will be 10 raised to minus 32 meters in size. We believe that we know that this part of the universe is governed by gravity. This part of the universe is governed by electromagnetic forces. This part of the universe is governed by nuclear forces. But we have no idea what governs the smallest and the largest in the universe. We have a dream called grand unified theory, but we have no idea what it looks like. But because the universe was born in a big bang, the smallest structure of the universe are connected to the largest structures in the universe. So there are people who study the largest structures in the universe in the hope of seeing the tail of the snake, or there are people who study the tail of the snake, the smallest particle they can imagine, to try and guess why the universe is the way it is. Another interesting thing about this picture is that this part of the universe is governed by plasma, low density material gradually moving around and deciding what happens. This part of the universe is governed by metals, in the sense that you cannot make a mountain out of carbon or silicon because it will simply crash under its own weight. You have to have metals like iron to make mountains. On the other hand, um, this part of the universe is governed by semiconductors, because there you can make small changes in the current and make the behavior change. So, for example, carbon is a semiconductor. The very source of life is a semiconductor. So, this part of the universe is governed by semiconductors. This part of the universe is governed by nuclear forces, but we really have no idea what governs the largest and the smallest structures in the universe. I can put it in another way. In our school syllabus, we call this as a subject of astronomy. We call this subject of geology. We call this subject of biology. We call this little window as a subject of chemistry. But essentially, it is all physics and mathematics that is simplified to a specific region, because you cannot always comprehend the whole universe together. And you cannot start talking about chemical reactions by talking of the universe as a whole. So we divide the subject into smaller things. So the universe was born 13.7 billion years ago, and it eventually formed the first stage structures, then the second stage structures. The sun is a third stage structure in which we have a planet which is able to support life, and that is why we have life. I am really short of time, so let me try and go to the next slide, which is to try, just as I did powers of 10 for physical universe, I can do powers of 10 in time. So 10 raised to 0 seconds is 1 second. If you go and light a torch to the moon, it takes about a second to reach. 100 times a second, your TV screen refreshes itself. So that is 10 raised to minus 2 seconds. 10 raised to minus 5 seconds is how long the sound remains on your ear when I speak before you, for you to fathom what it is. The ear responds within 10 raised to minus 5 seconds. 10 raised to minus 6 seconds is a megahertz radio signal. 10 raised to minus 15 seconds is the fastest laser we have seen. There are things happening on time scale smaller than 10 raised to minus 15 seconds, but we don't have the technology to know it. On the higher side, 10 raised to 4 seconds is the time you typically spend in a movie theater. 10 raised to 5 seconds is the duration of a day. 10 raised to 8 seconds is that how much time the Earth travels around the sun. 3 years, it's about 3 years. Human civilization has been around for 10 raised to 12 seconds. The time travels across the galaxy, light travels across galaxy in about 10 raised to 14 seconds. And the dinosaurs were around 10 raised to 16 seconds ago. And today the universe is 5 into 10 raised to 17 seconds. To look at it another way, we can divide the entire calendar of the universe into one calendar year. So the universe began on January 1, 0 hour, 0 minute, and 0 second. And today is 31st December, 23 hours, 59 minutes, and 59 seconds, going to the 60th second. If you do that, you get an interesting similarity. The universe was born, like I said, on January 1, 0 hour, 0 minute, 0 second. And today is 23rd December, 23 hours, 59 minutes, 59 seconds. The galaxies were born in February. It takes the universe a month after its birth to decide that it is born and start making structures. A whole of February is gone. It is only in February that whole of January is gone, and only in February they realize the mega structures of the universe. The sun and the solar system were created in late August, that is 4.5 billion years ago. So January, February, March, April, May, June, and July are gone before you get the sun, and that too in late August. Okay, 7 months after the birth of the universe, that you get the sun, the solar system. First life forms on the earth come up in September. So January, February, March, April, May, June, July, August, and September. 9 months after the birth of the universe, do you get first life on earth. Dinosaurs ruled the earth for about 500 million years, and that is simply rising in early December, and they died out in a fortnight. We've already come to December, remember that. Dinosaurs are born in early December and they die out in a fortnight. The first Homo sapiens, the Homo hominins of our kind were born on December 31st, 22 hours, 24 minutes, about a million years ago. That is 1 hour, 36 minutes within the year of the universe. The first human civilization appeared on December 31st, 23 hours, 54 minutes. We have been around as a civilization for 36 seconds out of 1 year of the universe. And I was born zero point 0.2 seconds ago. And if I live for zero point 0.3 seconds, I will have the average life expectancy of an Indian at 75 years or so. And there is no way I will live even zero point 0.4 seconds. 200 milliseconds in this 1 year of the life of the universe. That is all that I will be around for, or any human being on earth will be around for. The bottom line is that there's a poet who has said that a man said to the universe, "Sir, I exist." However, replied the universe, the fact has created no sense of obligation in me. The bottom line is that we are neither important to the universe from the size scale or the time scale, and we should always remember that. Thank you very much. Okay. So
Oh,
that is the lecture I wanted to talk about. I wanted to talk about the universe. I was asked to answer the question about how to um, become an
okay.
astronaut. Now, astronomy, there's something you must remember, that astronomy consists of, I mean, the study of space consists of three parts. One is space technology, space sciences, which worries about rockets and rocketries and satellite and interplanetary missions and so on. The second part is astronomy and astrophysics. Now, astronomy, astrophysics is an applied branch of physics. So you have to be very good in your physics in order to do your master's in physics first in any branch of mathematics, physics, and then go and study. You can do chemistry, by the way, because astrochemistry is as big a field as astrophysics, and astrobiology, of course, is a very big field of its own right. So you need to get a master's degree. A good institution helps, but it is not critical. What is critical is your commitment to it, your willingness to work hard for it, because nature is all encompassing. If you find it fascinating, by which you think of nothing else but the way nature works, you're bound to succeed. But you have to have full time commitment. If you think you can go to parties in the evening and have fun with friends, etc., and study only during school hours and pass with whatever 80-90% you get, you are not headed for career in science. Science is an obsession, and scientific career requires your full time commitment. If you're willing to make that, there is no joy like studying science, because it is new, it is exciting, and it is always fascinating. It is the only subject in which you are not doing the same thing for more than 5 years. Take any other job. Take banking, for example, take chartered accountancy. You're doing the same thing year in and year in and year out for decades together. And therefore, you get bored, and therefore, you need to go to parties and stuff like that just to get out of this boredom. If you are in science, you are forever changing what you're doing, because science essentially is a dialogue between you and nature. You ask your nature how something is happening, and nature tells you, okay, this is how I'm doing it. If you ask a trivial question, she gives you a trivial answer. If you ask a question that is very complicated, she'll give you an answer which you won't understand. So the whole field of scientific research is a field of dialogue with nature, and that has to be a full-time obsession. If you have that, then you should go for science, career in scientific research. If you want to worry about space and space technology, of course, you go to engineering degree and get an engineering degree in space sciences, space technology, aerospace engineering, and then you can join ISRO or any space agency. But if you're interested in how nature works, how nature on the huge size scale works, then you have to agree to make a full-time commitment, find a good teacher to study with, and spend your lifetime studying. That is the only way of building a career in research. It's a full-time obsession, and it comes at the cost of everything else. And you should be willing to pay this price to study for the rest of your life. You are never, I mean, we are called professors, but really we are never professors. Everybody remains a student for the rest of his life. So if you're willing to be a student for the rest of your life, by all means join the career of science, because there is nothing like career in science. I've been a scientist all my life. My engineering friends earned a lot more than me, and they had a lot of um, parties and funds, etc., while I was busy wondering how the nature is working. But I would not change my life for them. I would not give up my life for them, even though they have more money, because I have had fun and I have had insights in the working of nature, which you cannot get elsewhere. So think twice work about it. But once you have committed, work hard, find a good teacher, find a good school, find a good college, try and get into IITs or ICERs or whatever you have it. But that is not necessary. That is useful, but not necessary. You can still build your career if you are willing to commit your life to it. So if you wish to be a scientist, you are most welcome. Make a commitment for life and stay with that. Thank you very much.
Okay. Yeah.
If you have
So
any questions,
yes, sir, yes. So thank you so much, sir, for wonderful talk, which covered information about the universe at every scale. I personally like that with the scale of the universe, you also covered very interesting facts and a lot of useful details about the image. Okay. So I'm sure students have really enjoyed it. Now we have one question in the chat box from Samiksha Pandey. She is asking, you said that the sun is moving diagonally. Does that mean that the planets are moving diagonally along with the sun? Sir, you are on mute.
yes, definitely. So the planets are like shirts that we wear. Wherever the body goes, the shirt at the pant has to go. Similarly, we are completely gravitationally bound to the sun. So wherever the sun goes, we go with the sun.
Okay. Okay. Yeah. So thank you so much, sir. And I'll just like to make one announcement just about so this is regarding the tomorrow's lecture that we have. It is about the our solar system by Professor Siddharth Kasturirangan, and it will be up there the day after tomorrow. That is on Monday, 6 p.m. So all of you can join it. You will receive the link for the same. And again, with that note, once again, thank you very much, sir, and a huge thank you to the audience of such wonderful students who made this webinar very interesting and engaging. Okay. Thanks a lot, sir, and thanks a lot to all of you. Thank you and have a great day. Thank you, sir.
Thank you very much. Okay, bye.